Hello and welcome to another inorganic chemistry lesson. This time, we'll discuss how to deduce elements' oxidation states in the different compounds. For starters, let's look at the periodic table, because it holds all the information regarding oxidation states. If we look at the first A group, all elements in this group have an oxidation state of +1. The same applies to second A and third A. They have oxidation states of +2 and +3 only. From 4A to 7A, there are few positive oxidation states and always one negative oxidation state. For 4A, it's +4, +2, and -4. For 5A, it's +5, +3, and -3. For 6A, it's +6, +4, and -2. And lastly, 7A has a lot of positive oxidation states: +7, +5, +3, +1, and the negative oxidation state is always -1. Let's mention some exceptions that resides in A group. First is hydrogen. If hydrogen is formed a compound with a nonmetal, its charge is always +1. And with metals, it's always -1. For example, in a hydrogen bromide, hydrogen is +1 and bromide is -1. And in calcium hydride, calcium is 2 plus and hydrogen is -1. Nitrogen in a 5A group has a variety of different oxidation states, but the most important ones are -3, +2, +4, and +5. The next exception is oxygen. Oxygen's oxidation state is always -2. And lastly, we have fluorine in the 7A group, and its oxidation state is always -1. Now let's talk about transition metals. Usually, they are called chaotic elements because there is no correlation between a group number and an oxidation state. I will mention only the most common transition metals and their oxidation states. Chromium can be +2, +3, or +6. Manganese usually is +2, but can also be +4 and +7. Iron, nickel, and copper can be either +2 or +3. And zinc has only a +2 oxidation state. Lastly, silver is always +1, gold can be either +1 or +3, and mercury is +1 or +2. Here we have different chemical formulas, so let's determine the oxidation states of each element in these compounds. The first is H2O. As I mentioned before, oxygen oxidation state is always -2. Now what about hydrogen? Hydrogen always has a +1 oxidation state in the compounds with nonmetals. So if you remember the rules and possible oxidation states in the periodic table, you should be fine. Next is Al2S3. If we look at the periodic table, aluminum is in a third A group, so its oxidation state is +3. Sulfur must have a negative oxidation state, because in the compounds we have positive and negative particles. Because sulfur is in a 6th A group, its negative oxidation state is -2. What about Ca3N2? Well, calcium is in a 2nd A group, so its oxidation state is +2. And nitrogen in the 5th A group has a negative oxidation state of -3. Next we have CO2. Oxygen is always -2, but carbon positive oxidation state can be either +4 or +2 because it's in a 4th A group. What you need to remember is that in the compound we always have the same amount of positive and negative particles. In CO2, we have two oxygen atoms, each of which has an oxidation state of -2. So overall negative charge is -4. On the other hand, we have only one carbon atom, so that means that carbon should be +4 to balance positive and negative particles. What about Cl2O7? Once again, oxygen is -2. We have 7 oxygen atoms, so the overall negative charge is -14. That means that we also must have 14 positive particles. Because we have 2 chlorine atoms in the compound, we divide 14 by 2 and get 7. It is the oxidation state of one chlorine atom in the Cl2O7 molecule. The last chemical compound is SBr6. Bromine in the 7A group has a negative oxidation state of -1. And because we have 6 bromine atoms, overall negative charge is -6. We have one sulfur atom present, so its oxidation state must be +6 to balance negative and positive particles in the compound. Okay, so now we covered the compounds which have monatomic ions in their composition. Now it's time to talk about the compounds where polyatomic ions are present. Polyatomic ions are always made from 2 or more elements and have a specific negative or positive oxidation state. For example, sulfate ion oxidation state is always -2. The nitrate ion is always -1, and the PO4 ion oxidation state is always -3. If you can remember this table, you should do just fine with molecules where polyatomic ions are present. Let's look at a few examples. The first is Na2SO4. Sodium is in the first A group, so its oxidation state is +1. And from the table, we can see that the sulfate ion oxidation state is -2. Next is Al2SO3 times 3. Al is in the third A group, so we can write +3. And in the table, we can see that SO3 is always -2. Lastly, we have CaCO3. Calcium is +2 because it's in the second A group. And CO3 ion we can find in the table. As we can see, carbonate ion is always -2. The last thing I want to cover today is how to calculate each element's oxidation state in the compound when polyatomic ions are present. Let's take Na2SO4 as an example. Sodium is +1 and oxygen is -2. What about sulfur's oxidation state? As I said before, there are always the same amount of pluses and minuses in the compound. We have 4 oxygen atoms, each carrying a -2 charge, so the overall negative charge is -8. Sodium is +1, but because we have 2 of them, overall positive charge becomes +2. So we have 2 pluses and 8 minuses. So sulfur should be +6 to even out positive and negative particles. What about elements' oxidation states in HNO3? Hydrogen is +1, oxygen is -2. To find the nitrogen oxidation state, we calculate how many positive and negative particles we have in the compound. Oxygen in total generates a -6 charge, and hydrogen only +1. So nitrogen should be +5 to even out positive and negative particles. Next we have ZnClO4 times 2. The zinc oxidation state is +2 and oxygen is -2. To find the chlorine oxidation state, we calculate how many positive and negative particles we have. Zinc generates 2 positive particles. Now what about oxygen? If we have elements in the parentheses, we need to multiply subscripts inside and outside of the parentheses to get the total amount of atoms present in the compound. For oxygen, it is 4 times 2, so we get 8 atoms in total. Those 8 atoms generate minus 16 overall charge. So the difference between positive and negative particles is minus 14. That means that chlorine should generate 14 positive particles. We have 2 chlorine atoms in the compound because of the subscript outside the parentheses. So one chlorine atom has an oxidation state of +7. The last example is Al2CO3 times 3. An aluminum charge is +3, and like always, oxygen is -2. Aluminum generates 6 positive particles, 2 times 3. And oxygen generates 18 negative particles because we have 9 oxygen atoms in total, and each of them has an oxidation state of -2. The difference between the positive and negative particles is -12. So silicon should generate 12 positive particles. We have 3 C atoms in the compound, so 12 divided by 3 is equal to 4. The silicon oxidation state in aluminum silicate is +4. And that's it for today's lesson. Thank you for watching, and please subscribe to this channel for more chemistry content. Like always, I leave a few exercises with answers that you can do on your own, and see you in the next lesson.